Up to this point, you guys have done a lot of, I would say a little bit more simple integration kind of stuff. Today we're going to add in some stuff that's just a slight bit trickier, not much. But let's start off with a quick challenge. Can you do this one? Which you're probably looking at this and you're like, Mervin, that's not a challenge. What are you talking about? That's no big deal. The integral of 2 cosine x dx is simply just, well, I'm going to take the 2 and bring it out front. So 2 times the integral of cosine x dx. And I know the antiderivative of cosine is just sine, so this becomes 2 sine of x plus c. So actually not too much of a challenge, but let's talk about this one. 2 cosine 2x dx. What do you see about this one that looks different than the first one? We still have a constant multiple out front, so I can go ahead and take that out. 2 cosine 2x dx. But now, instead of just cosine of x, like I had before, I have cosine of 2x. So that's going to kind of throw a little curveball into the situation. So keep watching the video. At the end of this, we'll be able to do exactly this type of problem, and you'll know how to work it. So today's notes are about integration using U substitution. This is in 4.5 of your textbook, for those of you who like to keep track of that. But yeah, there's a new trick that we're going to add to our toolbox today, and it has a more informal name, but I'll see if you can come up with that informal name by the end of our notes today. Okay, so U sub makes problems a little bit easier that would normally be a pain. Like, for example, the integral of 2x times the quantity x squared minus 1 dx. So normally up to this point, how we would work this problem is I would just go ahead and multiply the 2x to both terms. And so this becomes 2x cubed minus 2x dx. And this is a very simple polynomial that I can integrate using reverse power rule. So this is going to become x to the 4th over 2 minus x squared plus c. I know you're probably thinking, again, Mervin, that was not that difficult. What are you talking about here? So I want you to look at this problem a different way. Okay, let's think about how, if I were to look at each of these as a separate expression. Okay, so x squared minus 1 is an expression on its own, and its derivative would be what? If I just took the derivative of x squared minus 1, that derivative would be 2x, right? Well, coincidentally, the derivative of that, is right here. Now, if I were to reverse that and try to take the derivative of 2x, well, that would be just a 2, and that's not located anywhere nearby. So because coincidentally I have the derivative of this expression right here, I'm going to say that this expression is my u. I'm going to say let u equals x squared minus 1. Okay, you're probably thinking, well, why are we doing that? And I understand. Just hold on for a second. Keep watching. Hopefully it'll make more sense. So basically what I want to try to do is I want to rewrite this entire integral, instead of in terms of x, all of it in terms of u, and hopefully a somewhat simpler format, so that way I can easily take the integral. So again, remember, I started out picking this one as my u because its derivative was nearby. So if I take the derivative of u with respect to x, I end up with 2x, which is right there. Okay, so we're off to a great start. What I want to do is I want to start my rewrite process, where I'm going to rewrite this integral, instead of in terms of x, I'm going to write it in terms of u. So I have the integral of this grouping right here was u. Now the 2x is here, but I also need to account for this dx, because when you rewrite an integral, whatever variable you have to have everything in terms of that same variable. So here my variable was x, now my variable is switching to u. Now u is an expression of x, but basically my new integral has to be entirely in terms of u. I cannot have any x's left over. So what I'm going to do here is I'm going to take this guy right here, and I'm going to kind of just modify this a little bit. So if I were to multiply both sides by dx, like so, well then these two cancel out, and I end up with du is equal to 2x dx. Okay, and you are allowed to do that. Yes, this is taking the derivative of u with respect to x, but these are also considered differentials. We don't get a whole lot into differentials in our class, but basically it's allowing you to go ahead and just multiply. You want to treat this like a fraction, so you can multiply by the denominator and move it to the other side. And we do that for situations like this, where now du entirely replaces both the 2x and the dx. So I can just take that and write du right here. Okay, so real quick, I rewrote x squared minus 1 in terms of u. Its derivative was 2x, and I brought over dx. So now, instead of having anything in terms of x, I have only stuff in terms of u. And this is a really simple reverse power rule situation. So u squared over 2 plus c, but I want to make sure that I finish my integral in terms of the same variable that I started with. So I'm going to replace that u with x squared minus 1 quantity squared over 2 plus c. So this is the same thing as what I had originally. Now I know it looks a little bit different, so let me prove to you that it would end up the exact same way. If I were to multiply this out using distribution, so I'm going to have x to the 4th minus 2x squared plus 1 all over 2 plus c. This is going to simplify to x to the 4th over 2 minus x squared. Now here I've got a plus 1/2 and then that plus c. Remember, anytime I have a plus c, it kind of just gets absorbed, and we would write that as all one constant. So this right here is essentially just plus c. Okay, so now when I write it like this, these two things match exactly with what I started with. Okay, so that's a real quick intro to u sub. Let's try another one and see if maybe it'll help click a little bit better. Again, that last one we could have done the original way, so you didn't necessarily have to do a u substitution, but let's try one that makes where u substitution is really a little bit more necessary. Again, for this one, I've got 2x and then x squared minus 1 in a quantity by itself, but it's being squared this time instead of just left alone. And so, old school way to do this, I would go ahead and multiply this out and then distribute the 2x and then do reverse power rule on all the terms, because I would just have a big polynomial. But let's see if we can do this using our new method of u substitution. So again, I want to look for the expression whose derivative is located somewhat nearby. So in this case, yet again, the derivative of x squared minus 1 is 2x. That's nearby. So I'm going to say let u equal x squared minus 1. So then du dx is equal to 2x. And then from here, I'm going to say du is equal to 2x dx. And I'm going to give you guys a little bit of a hint. Basically, anytime you do a u substitution, you're going to want to move dx to the other side. So if you wanted to, when you take the derivative with respect to u, you can go ahead and write 2x and then a dx next to it, or whatever the derivative is times dx, because we're always going to end up moving it. And that's an okay cheat, you would say. Remember, math people, we are not lazy. We are just efficient. Okay? So I'm going to rewrite this integral, again in terms of u. Now, the x squared minus 1 wasn't just by itself, but it's being squared. So I'm going to make that u squared. And then the 2x and the dx are being replaced by du. Now, I feel like some of you are probably a little bit concerned because they're not side by side, like I have them over here. Remember, with our rules of multiplication, this is exactly the same thing as x squared minus 1 squared times 2x dx. Remember, when you multiply, you can rearrange things in a different order, okay? 3 times 4 is the same thing as 4 times 3. So even though these are not quite in the same order, I can still make that change and say that the du right here still replaces 2x dx, okay? So now I've got an integral of u squared du, and I'm going to do reverse power rule on that, make that u cubed over 3 plus c, and then again replace u with my original x squared minus 1 cubed over 3 plus c. Okay, again, this one, if we had done it the long way, you would have ended up with the polynomial expression, which we still have a polynomial, we just don't have it all multiplied out nicely. We would have a longer polynomial expression that you would do reverse power rule on each individual term, and instead here we are just doing reverse power rule on one term, but that one term is in terms of u and instead of x. Okay, So let's try some more. We've got several examples here. Like usual, I want you to pause the video and try to give this one a shot on your own, and then come back to the video and see how you did. Okay, so hopefully you paused it. Now you're back. So again, this is 2x and x squared minus 1, but now it's within a radical instead of being squared or just by itself. So I'm going to say let u equals x squared minus 1 du is equal to 2x dx. Remember, we're just kind of cheating the rules here a little, not cheating, but skipping a step. Instead of saying du over dx, I'm just going to go ahead and multiply the dx over. So I'm going to go to my rewrite step, and now I've got u to the 1/2, and then the 2x dx is being taken care of by du. So then the antiderivative of u to the 1/2 is 2/3 u to the 3/2 plus c. So I've got 2/3 x squared minus 1 to the 3/2 plus c. Okay, now this is the type of problem that you really could not have done any other way, because unlike the last problem, the last two problems, you could have multiplied out the x squared minus 1 to whatever exponent it had. Here, because it's within a radical, there's nothing I can essentially do to this. I can't distribute the 2x inside a radical. That's not a legal math move. So the only way you could have worked this one was through a u substitution. Okay, let's mix it up. Let's try something different here. Ooh, trig. Yay. Okay, I know, it's everybody's favorite. What I want you to think about on this one, okay, is before you just do your u sub at random, and you probably want to write this down, okay, before you just pick any expression for u, you want to look for the relationship between your expression and its derivative. Okay, so here I see two different expressions. I see secant squared and I see a tangent of x plus 3. I say that these are two different expressions because this guy right here is grouped together by a parentheses, whereas this guy is outside of that parentheses. So if I were to take the derivative of secant squared, that would require the chain rule, because remember, the secant of x quantity squared is the same thing as this. So to take the derivative of that, I would have 2 secant x to the first, you know, just taking care of the 2, and then the derivative of secant would be secant x tangent x. Okay, that's a lot to swallow here. Like that's kind of quite a bit. I mean, I have a secant squared, but I already had secant squared. I want to look for something that is already there. Yes, I have a tangent, but there's no plus 3. So maybe choosing secant squared is not a great option for my u. Okay, so let's see if we can maybe pick a different expression for u. And some of you probably, I've already recognized, you're probably screaming in your head, Murphin, I know what it is. That's great. I'm proud. For those of you who are still a little confused, you know, you're doing okay. We already know that secant squared is not going to work. We just proved that. Let's talk about tangent x plus 3. If I were to let u equals tangent of x plus 3, I take the derivative of that, I get secant squared x dx. That looks a little bit more simple because now I've got tangent of x plus 3 would be replaced by u, and then this and this is replaced by du. So it becomes a really simple antiderivative situation. So I'm going to rewrite. I've got the integral of u, which is now tangent x plus 3, and then du replaces these two terms. Boom. Integral of u du. That's a reverse power rule situation. U squared over 2 plus c. So then now this becomes tangent of x plus 3 quantity squared all over 2 plus c. Okay, so although this problem looks a little daunting at first, it actually isn't too bad. Again, when you're doing u substitution, you want to look for a relationship between the expressions. One expression needs to be a derivative of another expression, or at least a slight modification of it. We haven't done too many modifications yet. We'll get to those a little bit later. Okay. Again, I want you to pause the video, give this one a try, come back to it here in a minute and see if you got the same thing. I'm hoping that you actually paused it and are now coming back. So when I see this one, I've got x squared plus 2 cubed times 2x dx. So this is one expression cubed. This is another expression. the derivative of this is 2x. So this is what I'm going to use for u. So let u equal x squared plus 2. Notice I'm not including the cubed in my expression. I'm only including what's inside the parentheses or inside the radical. That's intentional. Du is equal to 2x dx. So when I go to rewrite this, I've got the integral of u cubed and then du. Antiderivative of u cubed is u to the fourth over 4 plus c. So I've got x squared plus 2 to the fourth over 4 plus c. Okay? I hope this is starting to make a little bit more sense to you guys. If not, just keep watching. Hopefully within a couple of these it'll start to make some more sense. Okay? So let's keep on trucking here. So the integral of 3x squared times the radical of x cubed plus 1. Again, I've got two expressions. I've got this expression and this expression inside a radical. A good hint is the fact that this guy's inside the radical, so that's probably going to be u. And if I take the derivative of that, it's going to be 3x squared, which is exactly what I have on the outside. So let u equal x cubed plus 1. Du is going to be 3x squared dx. I can rewrite and make this u to the 1/2 because of the radical, and then 3x squared dx gets replaced by du, and I've got 2/3 u to the 3/2 plus c, 2/3 u to the 3/2, so u was x cubed plus 1 to the 3/2 plus c. Okay? All right, let's keep on going here. Let's see what else we have up. Oh, this problem. We had this one at the beginning of class today. Okay, so we want to look for an expression, two expressions, like one of them maybe inside some type of grouping scenario, and then its derivative. So here, a couple of ways to look at this. I can think of the 2 as an expression, the cosine 2x as an expression, or I can think of the 2 as an expression and then just the 2x by itself as an expression inside cosine. Okay, and the reason I want to do that is because if I were to make this guy u, well, the derivative of 2x is just 2, which is conveniently right there. Okay, so I'm going to say let u equal 2x, not cosine 2x, just 2x. So then du is going to be 2 dx. So when I rewrite this, I'm going to have cosine of u, because instead of 2x, I'm going to write u, so cosine u, and then 2 dx, so 2 dx gets replaced with du. And the antiderivative of cosine we know is sine, so sine of u plus c, so this becomes sine of 2x plus c. Okay, I told you we would come back to this one and you would know how to do this from last time. So I'm wondering if anybody has come up with the nickname for u sub. Okay, if you notice, if I wanted to take the derivative of this, what would I have to use? What, I don't want to say trick, but what tool would I have to use? Does anybody remember what I would have to use? Because I'd have to take the derivative of sine, but then I have to multiply by the derivative of the inside. That would be chain rule. So all of u sub is basically just the reverse of the chain rule. Okay, this is a perfect example of that. So let's keep going here and see. Hopefully it kind of starts to click a little bit better. Actually, this one is pretty basic. I will have it worked out and posted on Canvas for you guys, but I'm just going to skip this one for now so we can go to a little bit more complicated problem. Ooh, like this one, the integral of x e to the x squared dx. Okay, remember how I said you want to look for expressions that have its derivative or a slight modification of it nearby? This is that scenario, okay? So my expressions here, I've got x. I've got e to the x squared here. I could think of that as an expression, or I could just think of this right here of x squared as its own expression. And I want to do that because if I were to think of e to the x squared as its own thing, the derivative of e to the x squared is going to be e to the x squared times 2x. Well, and I don't have another e to the x squared floating around, so that's not going to work. So for this one, I'm going to say let u equal x squared. So du is going to be 2x dx. Okay, so I'm going to go to my rewrite step like I have before. When I rewrite this, I've got, let's see, the integral. Instead of e to the x squared, I'm going to make that e to the u. But now, oh crap, I can't just say du because du has a 2 in it, but my expression up here does not have a 2. If I were to just go ahead and write du right here, I would be making a mathematical error because I don't have a 2 that I would need to replace it with. Okay, so I just need this part right here to satisfy the x and the dx that I have left over. So instead what I can do is I'm going to multiply that 2. Actually, I'm going to divide by 2 on both sides. So I'm going to have 1/2 du is equal to x dx. Okay? Now, so what I did was I divided by 2 on both sides. So the 2 went away, and now I'm left with x dx. That's exactly what I need to rewrite this integral in terms of entirely of u. Now the catch is I've got this extra 1/2 out front, but that's just a constant multiple, so I can just put my scalar out front here and then write du right here. Okay, so now I've got 1/2 the integral of e to the u du. Well, that's just 1/2 e to the u plus c, so 1/2 e to the x squared plus c. Okay, so again, this one was a little bit tricky because we just had to do a slight modification of our du before we could substitute it in, but all we had to do was move around a scalar multiple and we were good to go. Let's see what else we got. Any more trig? Oh yeah, we have another trig one. Actually though, this is just like that 2 cosine 2x we did earlier, so I'm going to skip this one. Let's see if we've got, we'll do this one, 6 sine 6x. This is a little bit different. We haven't done antiderivative of sine just yet. So again, you want to look for an expression and its derivative nearby. I'm going to say let u equal 6x. du is going to be 6 dx. So rewrite the antiderivative or the integral of the sine of u, 6 dx, we're good there. Du, antiderivative of sine is negative cosine u plus c, so negative cosine 6x plus c is your antiderivative. Okay, so those are your notes over 4.5 reverse chain rule / u substitution. As always, if you need help, a lot of these examples came from the book, so check out 4.5, CalcChat, CalcView, Prof. Rob, Bob, Salcon from Khan Academy. All those are great resources. Either way, figure it out.